So our keynote speaker today, it is my great honor to introduce, is a retired NASA astronaut and former U.S. Senator. He was also part of the Apollo 17 crew. He is a geologist and the only professional scientist to have walked on the moon. Welcome, Dr. Harrison Schmitt. It is an absolute honor to have you with us today.
Well, it's my honor to be with you. It really is, and I appreciate the invitation very, very much. And what I'll try to do today is to just very quickly summarize what I think are some of the major highlights of the new science from Apollo, the legacy of Apollo. And in fact, in the back of your mind, you might be thinking that a great deal of the insights that have led to this came from the very first mission. The Apollo 11 sample collection, Neil Armstrong's observations, all led us to many of these insights that have been developed over the remainder of the missions and through 50 years of analytical research in synthesis that is ongoing. It's really quite remarkable how this continues to be, as I think Clive Neal and others have said, the gift that keeps on giving. Next, please. Let's look at the moon first. It was certainly the object of our affections for Apollo. Next. And next. The origin of the moon, there were many options early on when we started. We really have constrained those, I think, to two options. There's, of course, the giant impact hypothesis, which is the favorite of the most in the lunar community. And my own preference, though, is for a cold to hot accretion in the Earth's feeding zone. We can maybe talk about that a little bit later. Next, please. The internal structure of the moon has not only come from the information gathered by Apollo, but also subsequent missions, and particularly Grail. We can't forget that. The crust, 30 to 60 kilometer thickness crust now. That probably started out as more uniform, but has, because of the extremely large basins that have formed, South Pole Lacan and Procolarum in particular, it has been modified significantly. The upper mantle, probably about 500 kilometers down. The samples, we finally are identifying, I think, a few samples that have come from the lower part of the upper mantle, and the seismic evidence, of course, from Apollo and subsequent analysis has been important in that. Next. The lower mantle, below that, about 800 kilometers below the upper mantle, is apparently primordial. The volatile samples from the ash, the orange and black pyroclastic ash from Shorty Crater, are beginning, and other information is beginning to, I think, indicate that the lower mantle was never molten, and does preserve some of the primordial information about the origin of the moon. Next. And of course, there's a core around 350 kilometers in radius. There's been seismic, dynamic, paleomagnetic signatures, a number of independent indications of a core about that size, and one which for a period of time produced a dynamo and a global magnetic field. Next. Also, there has been a great deal of speculation over the decades about overturn of the upper mantle. I think it probably did not happen generally, but there's good evidence, I believe, now from Apollo 17 that the upper mantle did in fact overturn and brought samples of the lower mantle, of the upper mantle, near enough to the surface that large impact events like Imbrium could sample them and spread them to where we could find them, for example, in the Taurus Littoral Valley. The regolith has occupied a great deal of my attention recently. We have numerous samples, particularly a very broad collection from Taurus Littoral. Next. And that regolith is providing us with a detailed history of the near side lunar surface from about 3.83 GA. Next. It also provides a library of the sun, particularly the deep drill core. And if I was going to recommend something for the future, let's get a far more deep drill cores on the moon than we have to date. It is indeed, as Shoemaker told us decades and decades ago, it will be the library of the sun. And I think we're finally learning how to translate that library. Next slide. The resources for living in space certainly are included in that regolith. Basically everything we need in order to be self-sufficient, ultimately self-sufficient on the moon. Next. And then, as you know, one of my favorite topics is helium-3 fusion energy for Earth, clean energy here on Earth for the future. Next slide. Now, as I mentioned, we are looking at the regolith and particularly the deep drill core from Apollo 17 as a record of the history of the sun. And a couple items next that have come out of that is that the nitrogen 15-14 ratio increased by a factor of about 2 after 4.2 GA. We're still trying to define that more precisely, but there's no question that ratio was very different before there was a dynamo magnetic field, and very different than we see today. In fact, the del 15 nitrogen change from less than minus 200 per mil to today about minus 107 per mil. Really quite impressive difference, and probably represents an increase in N15 production in the sun's main sequence. Next slide. Next point. Next here. And also from that drill core at Apollo 17, we've been able to define that there was an increase in the energy of the solar wind by a little over a factor of 2, probably about 550 million years ago. We'll mention that again here in a moment. Next. And of course, one of the main scientific reasons and justifications for trying to understand the moon is to better understand the Earth, and particularly the early history of the Earth, which has been largely obscured to us due to the very dynamic processes that take place here at home. Next. The magma ocean concept that came out of the Apollo 11 samples indicated fractional crystallization of a global magma ocean, probably on all the terrestrial planets initially. Next. And I think we can look to the potential origin of the continents as a result of the differentiation of extremely large masses of impact, water-rich melt that occurred because of large impacts such as Procolarum and South Pole Lacan here on Earth, probably much more numerous, of course, on the Earth than on the moon. Next. As some of you are aware, I've looked in the past at the alteration of the impact debris of the Earth in a water-rich environment. Its alteration to synthetic cemented clay to give templates for the organization and chemical modification of organic molecules. This and there is some support for this hypothesis in what we have learned about the clay, the types of clay that are on Mars. Next. And it may be that this 550 million year old increase in the energy of the solar wind is responsible for the Cambrian explosion here on Earth, where the diversity of and quantity of life in the oceans exploded. Next slide. Now, as far as scientific exploration is concerned, we have quite a potpourri of lessons. Next. Political and commercial will to win the moon race is extremely important. We're almost certainly not going to go to the moon for science. entirely, it will be geopolitical, and we have to have that political and commercial will. Next. And of course, Saturn V capability or greater is really very, very important in order to efficiently conduct exploration of the moon, and also to reduce the number of risk factors that will be involved in conducting that exploration. Next. I personally believe we need non-solar powered spacecraft. They're just much more flexible in their utilization. They make the whole process much more efficient than if you depend on solar power for spacecraft. That's a personal opinion, obviously. Next. Apollo 13 through 17 geological training was extremely important in augmenting the sample collection, the description, the photography, on which we now depend 50 years later for continued understanding of the lunar surface and the planning of future activities there. Next. And next, telerobotic or automated experiment deployment is, I think, very important to increase the efficiency and utilization of human beings on the moon. The OSEP gave us a great deal of information about the moon. However, it took a great deal of time. Most of the first EVAs from Apollo 12 and on through 17. It could be done much more robotically and automatically than it was done. That's just was a mistake made 60 years ago, practically, and we need to rectify that in the future. Next. A dual capability rover will be very important. The Lunar LRV that we used on Apollo 15, 16, and 17 was very capable, worked extremely well. The people that put that together are to be complimented profusely. But we left it sitting there on the moon, and it, with a little bit of modification, could have been used for further exploration. And I salute NASA in their initial planning for a lunar terrain vehicle to have that dual capability in the future. But having a rover is very important. I think much more important to exploration than hoppers and the like. That decision was made that way for Apollo, and I think the logic for that is still very good. Next. And I would personally, with a great deal of bias, say that an experienced field geologist should be on every exploration mission. And with that, I'd be happy to take any questions that you might have in the time remaining.
Fantastic. Thank you so much for that great presentation. It looks like we have a question here in the chat. What is the evidence that the pyroclastic samples are volcanic in nature and not of other origin, including plasma electron events?
I think the primary evidence is the drive tube core that we took at Apollo 17 site at Shorty Crater. It gave us almost 70 centimeters worth of layers that the exposure ages, the GCR exposure ages, tell us that those eruptions occurred over a period of maybe as much as 200 million years, and that it also included pyroclastic gases, including water and other components that have isotopic signatures that appear to be primordial. I remember Jerry Wasserberg saying to me that he just didn't understand the lead data that comes from those samples. I think the best way to understand it is that it's coming from the upper part of the lower mantle, where we have essentially primordial materials preserved. There's also, of course, evidence for other pyroclastic eruptions at Apollo 17 and also at Apollo 16. These very low titanium ash materials that have been found at both sites indicate that there was another type of pyroclastic eruption. We have not really been able to study those anything like we have studied the pyroclastic ash from Shorty Crater, but nevertheless, the evidence is very strong that we also had very low titanium ashes erupted, probably in the same general time frame as the orange uh, glasses, but ashes. But again, it's difficult to study just individual particles when you don't have that in situ kind of geological information, field geological information that we were able to collect at Shorty Crater.
Right.
I have a
Thank you.
question.
It looks like we have several other questions here in the chat. What other capabilities would you like to see in a future rover?
Well, I think, as I mentioned, one of the things I'd like to see is that the rover can be a platform for an automatic deep drill. That would cause a great deal of stability. It was really quite a remarkable accomplishment by the commanders of the 3 missions that had these drills, the deep drill, in order to get that core. And as you know, the Apollo 17 core is nearly complete. We may have lost a little bit out of the top of it, but nevertheless, we have almost 3 meters worth of regolith ejecta zones documented now in that core. I think the rover can be an extremely important part of future automation of that drilling. So again, that you save the time of human beings for the kind of intellectual tasks that they're best capable of performing.
Great. And Ulf Israelson from JPL is asking, how much of an issue is lunar dust?
Well, it's a major issue. About half of the lunar regolith is less than 100 microns, as people know, and it is one which is going to take a layered defense against in order to solve. I think a good example of solving that problem was the lunar roving vehicle. It had no noticeable problems with dust in its bearings or in its operation, even though there were some anomalies. I don't think any of them have been tied to dust penetration. And so you can see that a defense against dust is possible there. Also, I hope that there are plans to continue to develop the extravehicular mobility units so that dust is rejected from the suit. As far as cabin concerns are concerned and habitat are concerned, the suit will be the EMU will be the primary vector of dust into that cabin, and the best way to deal with that is to have materials or systems that actually reject the dust. Fortunately for us, the dust does have some properties such as electrostatic properties and magnetic properties that will lend itself to a part of that layered defense that I've talked about through the decades. Yes, the one problem that I do not see a ready solution to yet, and that is dust getting into the connecting portions of various geological tools. Basically, those connectors stopped functioning for us on Apollo 17 in once we were into the second EVA. And getting connectors that are tolerant to dust is really going to be an important part of the engineering development in the future. And that would apply also to connectors that have to do with the transfer of volatiles and things like that. Another major challenge, of course, if we start to get into the extremely cold regions of the poles, is how to not only deal with ice and the potential of ice permeated regolith, but also how to preserve samples of that ice and get them back into the lunar receiving laboratory so they can be looked at as much in their in situ properties as possible.
Great. We have so many questions in the chat. We only have time for one or two more, and then hopefully, Dr. Schmidt, you'll be able to go through the chat and possibly answer some of those. There's so many. But this one I think is of particular interest to the community here. Based on your unique experience, what key advice do you have for someone returning to the moon now?
Well, make sure that you're well trained in exploration and field geology. That I think is the most important thing for the future as we try to develop new understanding of the moon as well as the Earth and the sun. That I feel very strongly about that, and I think the results of Apollo 17 uh, support that kind of a recommendation. But also, the main thing is to get there, and to get there with enough time and planning that new ideas in science can take root.
Okay, great. So do you think there's a strong case for perseverance, like rovers collecting samples and caching them for later human crews?
Well, I don't think there's any question about that. I'll say right from the beginning, I'm not a big fan of a personal uh, directed rover during crewed operations, but having precursors and postcursors that are rovers and are teleoperated is, I think, very important in enhancing the return from any given mission.
Okay. Well, unfortunately, we're going to have to conclude and move on to the next speaker. Or actually, did we have 30 minutes for this, Kevin? I believe so. I believe we may have 10 more minutes. So this is fantastic. Okay. So we have a few more questions then. You've previously described the smell of the dust after you entered the Apollo capsule. Others, like David Loftus, suggest the smell is an indication of the highly active surface of the regolith, perhaps a health hazard. What are your thoughts on this?
Well, I don't think there's any question that the gunpowder, spent gunpowder smell that everybody reported is indicates the highly activated surfaces of the individual dust particles prior to their being fully absorbing the moisture and oxygen in the cabin, the Apollo cabin. I think that's a good analysis, a good explanation for the smell. Uh, I personally, and the last three crews all had 4 inhalations of dust after each EVA, and then when we went weightless during the rendezvous sequence. To my knowledge, there's not been any indication that those 4 inhalations have resulted in any adverse physical issues. Now, there is an allergic reaction to the dust. I had a little bit of it. It gradually went away. But one of the flight surgeons who was responsible for getting the dust from the Apollo capsule, the Apollo 17 capsule, as a matter of fact, getting the suits from the capsule, had such an allergic reaction that he could not perform that task and somebody else had to do it. That is something we'll have to think about, and it probably behooves the medical community to have some kind of a anti-allergy inhaler available in the medical kit for future missions, just in case some individual has the kind of a much more severe reaction to the dust than I did. That and something more akin to what the flight surgeon had when he was working with those suits. Now, will long-term exposure be a problem? I think you have to decide that it would be. It has been on Earth, and we should plan to deal with that to keep dust out of the cabin by rejecting it on the surface, as I indicated earlier.
Okay. It sounds like it lends itself to furthering that development of personalized medicine for individual sensitivities.
It
Um,
is, but I'm not sure. I'm not sure you can ever completely personalize medicine. Sometimes things happen that you're not,
mhm,
you haven't decided. That certainly was the case in my case. But it is important to anticipate that somebody might have an adverse reaction, and to anticipate that very long-term exposure might create issues such as we see in silicosis here on Earth.
mhm. Very interesting. The next question from Dr. Pake. In addition to non-solar powered spacecraft, do you support nuclear power generator on the moon? Some experiments must operate through lunar day and night.
I do. I think there may be two or three options for long-term nighttime power sources, but a fission reactor on the moon certainly is one of them. We should not reject that out of hand. We certainly, I deployed a plutonium source for the RTG on the ALSEP, as did two other lunar module pilots with no adverse effects. NASA has launched RTGs on many occasions. They seem to be adverse to defending the use of nuclear power in space. I wish they were not. They've been successful every time they defended it. Yes, I think nuclear power is a very important option. I think fuel cells, a partially closed fuel cell cycle with solar power regeneration of oxygen and hydrogen is another option that should be looked at very carefully. We certainly have a very strong base in this space fuel cell technology, and we should not throw that away either. Uh, uh, Solar energy with batteries is another option, but one which I think, if you did the trade studies honestly and completely, might not uh, come out ahead of the nuclear or the fuel cell options.
Okay. And kind of switching gears a little bit, delving more into that geopolitical space you were talking about. How do you see the role of European and international science, engineering, and space communities coming together in applied lunar surface research for a future base?
Well, I think it's very important. The one thing I do think, though, is that there has to be very clear leadership in the basic infrastructure necessary to get to the moon and return safely. You've got to be very careful about what is in your critical path to success, and having that infrastructure in place then enables everybody to participate that wants to participate.
Mhm. Great. And it looks like we have a couple of questions related to your moon creation theory. And everyone is asking if you could elaborate on that.
Well, I just find and always have, frankly, the giant impact hypothesis increasingly complex to explain what I think we know geologically about the moon. What we know, I think, points to a relatively cool accretion up to maybe a radius of about 1,200 kilometers. And then, because of the conversion of kinetic energy to heat, the origin of a magma ocean during accretion by that process. Uh, and for the case of the moon, that represented another 550 kilometers with the differentiation of that magma ocean. I think very well documented now. It just again, it has to do with a gut feeling that we can explain what we know much more simply by a cold then hot accretion than we can through these very complicated computer models that support the giant impact hypothesis. They're really magnificent models, but I find it that they sort of violate the rule that what is the simplest answer is usually the right answer.
Absolutely.
And
So,
again, the isotopic evidence is that the moon accreted one way or the other, accreted in the Earth's feeding zone around the infant sun, and that also I think is a very important fact. That we've really had to work hard to find any differences between the isotopic composition of the moon and the Earth, and that in some sense does support something like a giant impact hypothesis, but it also just says accretion took place in about the same part of the solar system.
okay, and I think we have time for just one last question. Do you have any comments on the use of regolith as a growth media for bioregenerative life support systems?
Oh, I think that the regolith is going to turn out to be extremely fertile for a lot of different reasons, and that we ultimately, to support permanent settlements on the moon that are there in order to harvest its resources for use here on Earth as well as in space, that those settlements will have major agricultural facilities that will use the Earth as a growth medium, use the regolith as a growth medium. I think that that's entirely viable. And we have enough data, I think, from the early Apollo experiments to show that the regolith is quite fertile, and you would expect it to be. It's ground up rock, and it's never been it's never been farmed. It's very much like the great fertility that's given to the northwest portion of the United States by the volcanoes that have erupted up there. They provided fresh new nutrients that have supported the agriculture of those regions and regions all over the world, in spite of the risks that those volcanoes do pose to humanity.
Well, that is really interesting and actually really good news to hear. So, unfortunately, we have to wrap up. I think we could have kept you on here for hours, Dr. Schmidt. So much incredible information and thoughts to share. If you wouldn't mind taking a look at the chat, there are a number of questions that we weren't able to get to due to lack of time, but we can't thank you enough for joining us today and sharing your incredible background and all your thoughts for future missions to the lunar surface. And thank you again very much.
Well, thank you. I'll do my best to get to the chats, and I'm looking forward to Dr. Carrier's discussion here in just a few moments.
Fantastic. Thanks again.